Hi, so today in this video we'll discuss the extensive game with imperfect information. Okay, so this is the last type of game that we're going to introduce in this game theory series. Okay, so in this chapter we'll discuss the concept of of the extensive game with imperfect information. So it means that in those kind of games, each player when each player is taking some action, they might have only have partial information about the actions that are taken previously. Okay, and later we'll also see that this kind of framework it might be also helpful for us to formalize some ideas if some player they forget they might just forget what they have played before. Okay, and sometimes as we have seen previously in some of those Bayesian games where even the games are not in the extensive forms, although they're just strategic games, but there might be some incomplete information. But here we'll show the possibility of how we could use this sort of the very general framework in the extensive game with imperfect information to try to formalize the ideas that we have seen in those in the previous episodes. Okay, so this will be a very general framework that could incorporate all those previous cases, right? Because this will be the more complicated kind of game with imperfect information, and it has also a more general structure with extensive form, right? Okay, good. So let's start that. Extensive games with imperfect information. So normally when we are talking about imperfect information, we are always referring to some situation where if when this player is taking some action, this player might only have partial information about the actions taken previously. Okay. So let's take note. Player may have partial information on those actions taken previously. Okay. So those actions could be from other players or from themselves. Okay. All right. So if that's from other players, then this will also be possible to further incorporate the sort of the incomplete information where we see that in the Bayesian game, such that there is some state of nature or state of the world that is partially that could only be observed by some of the players. Okay. If let's say if this action is if some player doesn't remember their own action previously, okay, then this will be related to some definition or some result called perfect recall. Okay, good, and there'll be a bunch of interesting and useful results there that we're going to explore. Okay, good. So before that, let's first formally define the extensive game with imperfect information. Okay, so this will be a very general framework. Definition. So let's rigorously define an extensive game. Okay. So it has the following components, as we see in the textbook, in chapter 11, in Rubinstein and Osborne textbook. Okay, so if there's a finite set with players and players, right? Okay. And H again, it's the history. Okay. So empty sequence is also a member of H. Okay, is in H. Okay. And what else? Let's say if, so for H, it also needs some other requirements. So if the series, the sequence AK, K from 1 up to capital K, okay, if this is in H, so this capital K might be finite, and some L less than K, then this sequence from 1 to L, this must also be in H. Okay, so this is pretty similar to what we have defined before with perfect information. Okay, in the extensive form. Okay, so K from 1 to L, this has to be in H as well. Okay, so 1, 2, 3. There's 3 small points for this history. So third, if an infinite sequence, okay, if an infinite sequence, let's say AK from 1 to infinity, satisfies, let's say AK from K as 1 up to L, if this is in H, for each positive integer L, then we have this infinite sequence from 1 to infinity. This is also in H. Okay, good. So those are very technical requirements or the definitions that we need for this history. So essentially, each member of H is a history. Okay, so this H history is essentially a set of so this H is a set of the histories. Okay, set of histories. Okay, and N is the set of players. So those are all sets. Okay, and each component of history is an action taken by a player. Okay, and we have already known that, right? So a history is sequence A, K from 1 up to capital K in this set of history H. The sequence is terminal history if it is infinite or if there's no sum A K plus 1 such that the sequence up to K plus 1 is also in H, right? So it means that this is a terminal node or terminal history. Okay, so we don't bother to write those down. We know just know the meaning of that, right? Okay, so and also the set of actions available after the non-terminal history H, and that is denoted by this A, the set A. Okay, so now let's write that down. So we know, so here would be something terminal history. Okay. Maybe we should finish the definition, right? So terminal history, let's say this sequence AK, okay, from 1 up to K. If this is in H, and that is called terminal history if it is infinite or there's no some ak plus 1 such that this ak up to k plus 1 is still in H, right? And that's very straightforward. Okay, let's move on. And the A set, the set of actions available after the non-terminal history H. So the set of actions available after non-terminal history H is denoted by this AH. Okay, this is a set where this element H history and action A together. So this is in H, right? Okay, and because we need to put them together, right, as the element in the set of actions. And the set of terminal histories is simply denoted as Z, okay? Set of terminal histories is Z, okay? Those are just some notations. Good. So that's the history, all right? So that's a lot, right? Okay, good. So the next, we need to define the player function, right? So it means that after some point, at some point of history, then we need to know which player is the player to play next, right? So let's say a function P, player function, that assigns to each non-terminal history. So it means that assigns to each set that capital H excluding capital Z, right? And assign to that a member of, assigns H excluding Z, a member of, okay. So this N will be the set of the players, right? Okay. And union C, okay? So here, what do we mean? What do we mean is that, so this function P is the player function, okay? And this PH is the player who takes action after history H. Is the player taking an action after history H, okay? And let's say if this function, player function PH, if that equals to C, okay, then we say that chance determines the action taken after history H, okay? The action after H, okay? Good. All right, so that's the player function P, okay? And we also say that a function FC that associates with every history H with every history H, where PH is C, so that associates with every history H, where pitch is C, associates that a something, right? A probability measure FC given this history H on this action, set of action AH, right? So here what do I mean by this FC is that this FC is some probability of having this action A conditional on some history H. So that would be exactly the probability that this action A could occur after this history H, right? And this is also where each such probability measure is independent of every other such measure. Okay. Okay, good. So here, intuitively, FC A given H, so this is just the probability that this action A occurs after this history H, right? Good. So that's a probability measure for the action A after the history H. If only if this player is C, right? Good. So sometimes we call this chance as nature, right? So when we say nature moves, then this is simply some exogenous probability distribution that's given by some distribution, right? Okay. Good. So, and next, we're going to introduce something very important in the setup, which is called information partition, and that contains some information set. Okay. Those information sets are those things that we normally see in the game tree, where some dash lines connecting those different nodes, right? Okay, so now let's do this. So for each player I from N, let's say a partition or an information partition, calligraphic I of, okay, this is a partition of what? It is a partition of the history, okay, be careful, where this, a set of histories, where this history, it has to be the player, whose player is player I, okay, going to move. All right, so, and it satisfies some property such that this AH, okay, equals AH prime whenever H and H prime are in the same member of the partition set, okay? Now let's first finish this definition and then go back to explain this, okay? And in addition, for those elements in the partition I, in calligraphic I, then we denote by A of capital I, the set AH, and denote by P of capital I, the player, of course, PH for any history in this capital I of player I. Okay. So here, what do we mean by this very technical definition? And later we'll show some example of that, and that'll be very straightforward. So here, intuitively, we want to talk about that. So here, this calligraphic I is exactly the information partition, okay, for some player I, and the element of calligraphic I, so the set capital I in that is exactly the information set that we are talking about here, player I. Okay. So later we'll use a very simple example to illustrate this idea. Okay. So for now, we just leave it there, and move on to the next requirement for this definition. Okay. So finally, what we're going to define is the preference relation. Okay. And we still, as before, we still define this preference relation over the terminals. Right. So for each player I, we say a preference relation. Okay. On the lotteries will be simply referring to the expected payoffs, right? Or the expected utilities with some probabilities, right? Over the terminal node Z, as we just defined previously, right? So this is the preference relation of player I, okay? And that can be represented as we just mentioned, as the expected payoff or the expected value of a payoff defined on this terminal Z. Okay? Good. So put it together to wrap up. So we say that the tuple N, player set N, a set of history H, and player function P, and the nature's probability measure F, and this calligraphic I for player I as the information partition, including all those information sets for each player I, and altogether this, and of course the we'll put the preference relation later, right, if we need that. So all those together, this forms that constitutes this extensive game form, right, or extensive form game. Okay, if they satisfy all those definitions or those conditions as mentioned before. Okay, good. So now let's move on to some example. Okay, as illustrated in the textbook on the page 202. So this would be a very simple example in an extensive game with imperfect information, right? So now let's have a look on this game tree and try to figure out those player functions and those information partitions, right? So those would be the most difficult, most abstract definition they're going to understand, right? Okay, so now let's draw this game tree. So this would be on page 202, and it's the figure 202.1. So an intensive game with imperfect information. Okay, so let's say player 1 moves first and has 2 possible actions, left or right. Okay, so if plays right, then this game ends with 2 and 1. If L, then game continues. Then player 2 gets to move. So there will be also 2 actions, A or B. Okay, so here we have a so-called information set for player 1. So here we connect all those using the dots or the dash line here to connect those two non-terminal histories, or connect those two nodes, and write player 1 on top of this dash line to indicate that this is the information set for player 1. Okay, so it means that player 1 actually doesn't know that whether player 2 is playing A or B. Okay, so here then the game moves as follows. So here player 1 chooses either L or R, little l or little r, as the last move. Okay, if AL, then the payoff will be 0, 0. If big L, A, small r, this is 1, 2, and here is 1, 2, and 0, 0. Okay. Okay. Good. So, and we need to draw all those black dots. And here is a circle, right? It's empty circle. All right. So this is the game tree. Okay. So that shows an example of extensive game with imperfect information, right? Because there's some information set. So in this game, player 1 moves first, choosing either L or R, capital L or capital R. If player 1 chooses capital R, then game ends. But if chooses capital L, then player 2 moves. So player 2 knows that if player 1 chooses L, then player 2 could choose A or B. Okay, so in either case, it's player 1's turn to move, but player 1 here cannot observe player 2's action, either A or B. So we simply use those dotted lines to connect those ends of the histories after which player 1 has to move for the second time here, right? To choose either little r or little r, okay? So formally, we write down those notations so to have some intuitions for the definitions we had just earlier. So what we have is that the player function with empty set should be player 1, right? And with after the history L and A is also player 1. After L or B, L and B, this is also player 1, right? So those will be all equaling to they are player 1, right? Those player functions. Okay. So player 2's player function with input as L, it will be player 2, right? And nothing else. Okay, so how about the information partition, which is the most abstract part in this case? So calligraphic information partition for player 1 would be just a big set that includes all those information sets. So the first information set would be this empty set that is indicating the start of this game, okay? And the other information set that player 1 has is LA and LB, okay? So here it means that player 1 that cannot distinguish whether this is the real history or this is the history, right? So those two together, they form some information set, and right, so this would be the information set that player one has, and this empty set, the set of empty set, will be the other information set that the player one has, right? Because player one moves in total twice, right here. So player one has two information sets in this game. Okay, and for player two, it'll be very simple. So calligraphic 2, I2. So this will be simply the set. So we put this big brackets, and then there'll be only one element for that. Okay, so there'll be simply this L. Okay, and we put that in the set. Okay, good. So here player one has two information sets, but player two only has one. Okay, and those numbers here after the terminal histories are just players' payoffs, right? And normally the first number is the payoff for the first for the player one, and the second number is for player two, right? Normally. Okay, good. So this is a very good example of the extensive form game with some imperfect information. So later we'll see that, for example, so this is so here when player one gets to move for the second time, player one doesn't know the exact action taken by player two, right? But sometimes in other kinds of games, we might see that some players even forget. They might even forget what they did before, okay, by themselves. So, for example, and later we'll introduce this kind of game in a full-length episode. But here we'll show some example where, for example, if player one moves first and player one moves second as well, so there'll be only one player in this case. So if player one takes right, then the game ends. But if player one takes left, and the game continues. Okay, and if player one, so this is player one and player one again. If player one chooses, let's say left, and it goes here. If player one chooses right, and it goes here. Okay. So what do we mean by this imperfect recall? Right, we'll informally introduce this in the next episode. But here, if this player one doesn't remember what they did before, so we simply need to use the dash line or the dotted line to connect those two histories, right? So this is very interesting. So that simply means that the player one doesn't even remember their own previous history or own previous action, right? Okay, good. And we'll formally introduce that in the next episode. Okay, good.